Hello everybody, this is Dr. Christopher White and welcome back for part 3 of Paleozoic Earth history, focusing on the early Paleozoic. So before we go any further, let's just quickly get the code word out of the way. The code word for this presentation is unicorn. I repeat, unicorn. So U-N-I-C-O-R-N, unicorn. So please make sure you write that down, put it somewhere safe because you're going to need it for the code word quiz. So what happens at the end of the Tippecanoe sequence? So by the early Devonian, the Tippecanoe Sea is going to have regressed to pretty much the original starting point, and as we've also just discussed, it will have left behind a few what are called interconnected basins. So these will be these isolated small bodies of water which are left behind in depressions, which will then just evaporate away over time. So the craton was weakly deformed during this period, producing domes, arches and basins. So the Tippecanoe sequence is going to be very, very gently folded during this time. We're not talking really big, large-scale deformation that's going to give you mountains. We're just talking quite gentle deformation that's going to just cause the Tippecanoe layers to undulate a bit. So where we have areas of the crust being pushed up so they become high ground, that's obviously going to encourage those areas to be eroded, and this is obviously going to lead to the formation of fresh sediments, which are then going to be transported via large rivers to the coasts where they will be deposited. And obviously some of these areas of higher ground will be exposed during the next Cratonic sequence, which is going to be the Taconic Sea, and that's going to begin forming in the Middle Devonian. So some of the rocks which are being deposited and formed during the Tippecanoe sequence are then going to be eroded to produce, or at least yield, sediments which will be deposited into the Taconic Sea. Okay, so that was the two Cratonic sequences, so the Soc and the Tippecanoe, that formed during the early Paleozoic. So now we need to start thinking about mobile belts and orogeny. So what was going on in terms of plate tectonics? So the Appalachian Mobile belt began forming during the Middle Ordovician. So it started forming a very long time ago. So the mountain building was part of a broader tectonic regime that sutured the continents together to form Laurasia by the late Devonian and Pangaea by the end of the Paleozoic. So if you remember, Laurasia is essentially Laurentia plus Baltica. Okay, so Baltica of course is Western Russia and Northern Europe, mostly the Scandinavian countries. And obviously Laurentia is North America, Greenland, a bit of Ireland and a bit of Scotland. And so those two land masses together form the supercontinent of Laurasia. And of course in the southern hemisphere we had the supercontinent of Gondwana. That is of course South America, Africa, India, Australia and Antarctica. And eventually those two supercontinents are going to hit each other towards the end of the Paleozoic. So in the Carboniferous and Permian, they're going to be running into each other. And that's, of course, going to give us the supercontinent of Pangaea. So in the late Paleozoic to early Ordovician, the eastern margin of Laurentia was passive. So it was nice and boring, nothing exciting was going on. And the eastern, well, what is now the modern day East Coast would have represented the western margin of the Iapetus Ocean. So just imagine that the Atlantic Ocean wasn't there, and instead rename it the Iapetus Ocean, and that would be essentially exactly the same situation. Now, in terms of the Iapetus Ocean, it was opening to the east and the southeast. So once again, just like the modern Atlantic now, we would have had a spreading ridge down the middle of the Iapetus Ocean, and that would have been creating new oceanic crust. So in the Middle Ordovician, a subduction zone opens up in the Iapetus Ocean basin, and it starts to destroy the seafloor of the Iapetus Ocean. So obviously we're going to start to see the Iapetus Ocean getting essentially destroyed as the seafloor gets subducted, and that's going to start bringing the pieces of continental crust on either side of the Iapetus Ocean together. And this is going to be the first stage of the formation of the Appalachian Mountains. So here we go, this first stage is going to be right here in the middle to late Ordovician, and it's going to be the Taconic orogeny. So here's our situation. So here's Laurentia. So obviously we've got North America here, Greenland here, you have Scotland there, and Ireland here. Okay, obviously we have a body of water that's coming down here. This is our Iapetus Ocean. Now please remember, this diagram is orientated for the modern orientation of North America. During the Ordovician, Laurentia would have been essentially 90 degrees. So what is now the modern day west coast of North America would actually have been the north coast. The Gulf Coast region would have been the west coast. The modern day east coast would have been the south coast. And the modern day northern coast of North America would have been the east coast. Okay, so just take Laurentia and just flip it 90 degrees. So the top is now over here, essentially where the east coast would be. So this entire image should really be flipped 90 degrees. Anyway, so what's going to happen is we have the Iapetus Ocean here. We've opened up a subduction zone on both sides. So we're destroying the seafloor, and this is allowing Baltica to move towards Laurentia. So when those two hit each other, we're obviously going to form the supercontinent of Laurasia. And we also have an additional piece of continental crust. This is the microcontinent of Avalonia. Okay, and the microcontinent of Avalonia consists of parts of New England, most of what is England and Wales in the United Kingdom, and parts of Eastern Europe. So what's going to happen obviously is the subduction zone is going to slowly destroy the Iapetus Ocean basin, and eventually these pieces of crust are going to hit each other. So this is our basic situation. So it's a very simplified diagram, I know, but this is pretty much what was going on. So here's Laurentia, and here's Gondwana. So at this particular moment, Gondwana is actually going to be down here off to the side. So you can actually replace Gondwana with Baltica, but essentially it's the same process going on. So you can't see Gondwana in this image, but it is there. So what's going to happen is we're going to form a subduction zone off the coast of Laurentia. So we're going to start forming a subduction zone out here, and it's actually going to be subducting the seafloor which is attached to Laurentia underneath the seafloor of the Iapetus basin. Okay, so we're going to end up forming an island arc in the middle of the Iapetus Ocean produced by this subduction zone. At the same time, we also have another subduction zone operating over here along the coastline of Baltica, Avalonia, and even though it's not in the picture, to the south you're also going to have a subduction zone operating along the coast of Gondwana, and that's also going to produce an island arc. Now what's going to happen obviously is this seafloor here is going to be slowly destroyed and subducted, and this is going to bring Laurentia to the west, and eventually it's going to run into this island arc here, and that's exactly what happens. So Laurentia is going to crash into the island arc, and so what we're going to end up with is a mixture of this grey stuff. These represent essentially detrital marine sediments. You're going to have a mixture of volcanic rocks as well, which are related to the volcanism. So you're going to have things like rhyolites, andesites, and granites, which represent the magma chambers which fed the volcanoes. And all of that stuff is going to get mashed together, and it's going to give us the Taconic highlands along what is now modern-day east coast of North America. Now, once this happens, we're going to get a subduction zone forming under the east coast of Laurentia, and this is obviously going to allow what's left of the Iapetus Ocean seafloor to steadily be destroyed, and that's going to bring both Baltica, Avalonia, and Gondwana towards Laurentia. So the collision between Laurentia and the island arc caused by the island arc and marine detrital sediments produced by volcanic activity causes them to be thrust onto the continent, producing the Taconic orogeny. So the Taconic orogeny essentially is where this island arc plasters itself onto the modern day east coast of North America. So subduction then switched direction to under Laurentia, producing a chain of highland volcanoes which ran from Newfoundland all the way down to Georgia. So the one thing about the Taconic orogeny is that it's situated along the modern day east coast of the United States. There's actually going to be another orogeny that's going to happen further up. That's going to be called the Caledonian orogeny, and that's going to mostly affect the rocks which are now part of Canada and Scandinavia. So the Appalachian Mobile Belt, of which the Taconic orogeny was the first step, developed in a region that had been essentially a very shallow carbonate platform which stretched from Newfoundland to Alabama. So we had this nice, quiet, passive continental margin. And this continental margin was part of the Sauk Sea. So the shallow marine carbonates contain stromatolites, mud cracks and shallow marine fossils. So we know that that must have therefore been a shallow water environment. But then we see these shallow water carbonates start to get covered by middle Ordovician sequences containing clastic marine sediments, so muds and sands. And so the deposition, or should I say the formation of these clastic marine sediments, is indicating that we now have land that's being pushed above sea level so it can be eroded. And so this is showing us that by the middle Ordovician, we know the Taconic highlands must have formed along what is now the modern day east coast of the United States, because we shift from this shallow water carbonate environment, which is pretty much clastic sediment free, to an environment by the middle Ordovician which is clearly clastic sediment dominated. So we have lots of sands and muds being deposited as the Taconic highlands are eroded. So this is going to help us to time the formation of the Taconic highlands. So it's telling us by the middle Ordovician the land has been pushed above sea level and is therefore being eroded. Along with these sediments, we also have volcanic deposits which are telling us that we have volcanism going on. So the two of these combined mean that the event itself must have therefore started in the early Ordovician, because it takes a while for the land to actually be pushed above sea level. And so that means the Taconic orogeny must have started in the early Ordovician, and we begin to see the signs of the highlands themselves being pushed above sea level by the middle Ordovician. So the deepening of the carbonate basin on the Appalachian Mobile Belt's western margin resulted from downwarping of the crust due to subduction. So if you think about the Taconic highlands, which are going to be located essentially along what is now the modern day east coast of North America. What am I saying? It's this picture down here, I do apologise. So here's our Taconic highlands over here. So we're going to have a subduction zone running along the east coast here, so that's going to be an active margin. And then on the western margin, we're going to have a passive margin. Okay. Now, this basin here is going to be formed through what's called downwarping. And essentially, this is where the crust on the backside of the highlands essentially begins to be pulled down and stretched as part of the subduction process. And it creates a depression in the crust, which is naturally going to, in this case, fill with seawater and sediments which are being eroded off the highlands. So the paleo current direction, so when we look at the sediment, we can tell which way the sediment was being deposited, where it was coming from and where it was going. We can see based on these paleo currents that sediment was being transported from east to west in this basin. So our basins are going to be right here along the western coast, and we can see the sediment is forming in the east and it's moving westwards. And this once again is consistent with the formation of the Taconic highlands along the modern day eastern coast of the United States. And obviously we know on this side we've got the active margin, so that's not really going to have a particularly great sedimentary sequence. But on the passive side over here, we're going to have sediments being eroded and transported from the east to the west. So the timing of the Taconic orogeny is actually quite well constrained. We know this because we can also look at rocks which are lower to middle Ordovician in age, and we can see these rocks have been tilted. And because they've been tilted, well, that's obviously part of the mountain building process. So we have evidence that shows by the middle Ordovician we have clastic sediments being deposited. That tells us the Taconic highlands were above sea level. And we can see we have evidence from lower Ordovician rocks that those rocks were being deformed. So this is telling us that even before the Taconic highlands broke above sea level, the rocks were already being deformed in the lower Ordovicians. This is telling us when the Taconic orogeny started. So the rocks which are deformed by the Taconic orogeny are then unconformably overlain by horizontal to shallowly dipping Silurian age rocks. So this is telling us by the Silurian the Taconic orogeny is done. It's over, the mountains have stopped growing, they've been mostly eroded away, and then a new layer of Silurian sediment is deposited over the top, and those layers of Silurian sediment are pretty much horizontal. So we therefore know that Taconic orogeny must have started in the lower Ordovician, okay, and it probably finished by the early Silurian. We can then also back this up even more by using radiometric dating of ash layers associated with the volcanism which is produced by the Taconic orogeny, and we can date the volcanic rocks, we can date the intrusive rocks associated with the magmas which are feeding those volcanoes, and those rocks give us a date of middle to late Ordovician. And so this is telling us that the orogeny started in the early Ordovician. By the time we're into the middle Ordovician, we have the Taconic highlands actually above sea level being actively eroded. We also know they are volcanically active. We know this continues into the late Ordovician. And then as we transition into the Silurian, we see the Taconic orogeny stop. And so this is our basic situation. So this represents the situation before the Taconic orogeny. So over here we have Laurentia, over here we have Baltica. Here's our oceanic crust, the Iapetus seafloor. Just think of it like the modern day Atlantic almost. And we have a spreading ridge in the middle, which is creating new oceanic crust. Now we know that a subduction zone opens up on both sides of the basin. And so this is going to destroy the Iapetus seafloor, so it's going to be subducted away underneath Baltica and Laurentia. And this eventually is going to lead to the continents hitting each other. And this collision is actually going to be mostly focused up here in northeastern Canada. And that's going to produce a set of highlands called the Caledonian Highlands. Now down here we have the Taconic highlands. They are actually more related to island arc action. So this is going to be island arcs which are part of the larger Baltic terrain, are going to be hitting the modern day east coast of the United States, producing the Taconic highlands. So the Taconic highlands aren't technically a continent-continent collision. You should think of them more as a continent-island arc collision, kind of like Japan running into the east coast of North America would be a good example of the kind of situation that would produce what we see. So we end up forming what's called a clastic wedge along the western margin of the Taconic highlands. So we've discussed that sediment's going to be eroded off the Taconic highlands here, and it's going to be deposited along a passive margin here. And this is going to form a clastic wedge. So the same sediments would have been deposited along the eastern side of the Taconic highlands. However, as we've discussed, this side was active, and as such those sediments aren't really going to be preserved too well. So the sediments that make up the wedge are thickest and coarsest near the highlands and become thinner and finer as you move away. So we have a wedge of material that starts essentially on the coast here and progresses westwards. And this wedge of material is thickest and coarsest here, close to the highlands, and it gets and the class size decreases as you move away. And this makes sense. Obviously, if you have sediments, you're depositing them, you'll deposit the coarsest sediments closest to the coast, and the finer sediments, because they're naturally lighter, will be able to progress further into the ocean basin. And that's totally normal. Now, the fact it's called a clastic wedge is simply because it produces, if you were to take a slice through it, a distinctive wedge shape. So the sediments would have essentially would be quite thick here, and they would steadily get thinner as you headed westwards, and that gives you this triangular shape. So the clastic wedge produced by the Taconic orogeny is called the Queenston Delta. So here's the basic idea. Here's our Taconic highlands. Here's essentially our basin. Now in this case you can see it's been partially filled in by sediment coming off the Taconic highlands, but nevertheless, so this area here represents an area of seawater, so the basin, that's being filled in by sediments coming off the eroding Taconic highlands. And this sequence of sediments will be thickest, closest to the highlands, and it will steadily get thinner as you move away, and it will form a crudely triangular shape. So mapping of the delta indicates that around 600,000 cubic kilometers of rock were eroded to make it, and such a volume would suggest that the Taconic highlands were at least 4,000 meters high, so that would put them at the same kind of scale as the modern day Rocky Mountains. So the Taconic orogeny marks the first stage of the mountain building process, which is going to, essentially form the Appalachian Mobile belt. And things are only going to get more fun from here, because eventually we're going to have the full-on collision between Laurentia and Baltica, and that's really going to produce some very fun plate tectonics. Okay, so that's it for this presentation, so thank you for watching and take care.